You're listening to the Not Just Numbers podcast, a conversation with mathematicians on their work and their lives to get to know them and discuss common biases and misconceptions. Hi everybody, welcome to the new episode Talking Mathematics to Strangers. Next to me there is Marit van Straaten, our host.
Hello.
And with us today, Julian Koellermeier and Roland van der Veen. Thank you very much for coming here. And as usual in the podcast, we start to learn something about our guests. So I start with Julian that is sitting on my left. And can you tell something about who you are and what you do, said in a way that would make some young people that know nothing about mathematics happy?
Yeah, thank you, Marcello and Marit, for inviting me. Happy to be here. So my name is Julian. I'm a colleague of you, and I work at the University of Groningen. I'm an assistant professor. I work in applied mathematics. That means that I work mostly on applications where mathematics can be used. In my case, the application is in aerospace engineering. So that means that my concrete research is in math, but I work on, for example, spaceships that go through the atmosphere and then they want to enter the atmosphere and land on a planet, for example, on Earth or on Mars, potentially. And this is difficult because the spaceships are very fast and they want to land safely on the planet, and they need to slow down to land safely so that they don't crash. And then they get very hot because there's a lot of friction with the air. It's like when you go with very fast to the wind, then there's a lot of air that hits you and that makes you very hot and you don't want to burn up. So you need to protect the spaceship, and you need to know this before you start the spaceship if you can land. So we need to, with mathematical methods, compute beforehand if the astronauts in the spaceship can safely land and the rocket can land. And this has also applications in other domains. For example, it's not only about air and spaceships, but it's also about ships and water, for example, or waves that go through the ocean. And then you want to protect the coastline, and this you need to predict before with mathematical methods. How high will the wave be? How severe will the coastline be destroyed? And to compute that. And my work is about making mathematical models, so a representation of reality, so that we can test if the wave will hit the coast or if the spaceship can land, and do that with mathematical methods.
Sounds really, really interesting.
To me too, yes. Yeah. That's why I do it.
Yeah. I also really like planets and stuff. Mm-hmm. How did you get into this topic? Was it because of your interest in that field, or? Yeah,
so it's a long story, of course. And I actually never really started studying mathematics. I started studying engineering. And in engineering, I found out I like the math much more than the actual engineering part. And then I took the part that is with the most mathematics in engineering. This is aerospace engineering. And then I got more sucked into the mathematical beauty of equations and numbers. And then I majored there. And in the end, I also did my PhD in applied mathematics, shifting more and more to the mathematics side, but always on the applied side. Because that was very important for me with my background as an engineer. And at the moment, I'm not really working on the application itself in the sense that I'm not building a rocket or I'm not building a dam or anything like this. But it's important for me to have it sort of in the background or at the back of my head that this might be useful for that eventually.
I can imagine that having a purpose to the mathematics that you're doing is really helpful for your work. Yeah. Even though in the day-to-day business, you might be working on papers and on theories and on complicated formulas, and you might sometimes wonder, okay, where is this even used? But in the big picture, we will get to this later, because when you communicate science to other people, then it's about more the big picture, not the nitty-gritty details of a formula that you want to explain. So then you at least have the big picture always behind you that you can rely on. Yeah.
What particularly excites me about what you're saying in this episode is that I think it's the first time that we really have a pure mathematician and an applied mathematician, if you allow me to use this term, sitting together at the table and talking about the math that they like and talking to people. So I'm curious to hear Roland's, what you're doing, what's your point of view of this?
Well, thank you for having me. My name is Roland. I'm also a colleague, just associate professor here. In geometry, maybe. What I like to do is tie knots. So just picking a piece of string and just fiddling with it. I don't know if this is pure or applied, but it makes me happy. And I think that's the most important thing. But this is actually a serious subject in mathematics, and it's related indeed to the fluids that Julian was just describing, and space and the nature of space. But maybe my interest is more from an art point of view, or even a meditation point of view. I really like to compute as a form of meditation, maybe. So this was already in primary school. I just enjoyed doing calculations because it made me sort of mellow. So that was just numbers, but it's even better with shapes. So I like to think about, if you have 1 million triangles, what kind of shape can you build with 1 million triangles? You can build lots of, but if you just randomly plug them together, what will you get? What will you get? A sphere? Will you get a rabbit? What will you get? So this is some of the things I like. And studying shapes by knotting a piece of string is another. Some are very applied because you can do it with your hands, but also very pure because anything goes. And it's really just by building a fantasy castle out of thin air. This is what I like about mathematics. And so I've been doing that, as long as I can remember, I suppose. When I was a student, I wanted to be a computer scientist because I thought programming was the way to build everything. But then I realized that you can just use your mind, and that's even better than hardware. Because hardware is always broken, and you have to load libraries and whatnot. Yeah, so just out of pure thought, creating something and then putting it on a computer. So in that sense, I kind of disagree with your split in pure and applied mathematics, because much of my motivation also comes from cooking, like stirring in a pot. You see these fluids that swirl. And that's very motivating to me as well. But is this pure? Is it applied? I'm not sure, but it's good math. And that's what I'm looking for.
Oh, I fully agreed with that. We are going to have 2 episodes, one on pure math and one on applied math. And my true hope, since we record them next week, I can say it because they won't hear this episode by the time we record it. But my true hope is that we will come up by saying that there is no pure or applied math and there is just math. Mm-hmm. I pretty much agree with what you're saying.
Good math and bad math.
I don't even think that there is that bad math. There might be wrong math in the sense full of mistakes, but I think overall it's just math, and those mistakes are what will lead you somewhere else.
Definitely.
Yeah, I also think that mostly the benefit of, or like the advantages of, and the advances of working together should be emphasized, because the interesting part is when you mix the application with the theory, or the more applied stuff with the underlying stuff. And then when I do very applied things, and when it's about a real object that needs to fly, then there are some theoretical questions. But the people from the application side, they cannot answer them because they don't have the theoretical background. They don't want to learn this. And then the more theoretical people, they say, okay, that's a nice application. It's like a problem, maybe a toy problem for them, or like a boring problem or so, but at least they can apply their theory to that problem. And then something new is generated. And I think this is always where we generate new things. So we need to talk together and sit down just like here and then exchange our points of view.
I agree that you make a really good point, Julian. I was also wondering, did you guys always know that you wanted to pursue a career in academia, or did it just happen?
Yeah, so for me, I always wanted to just see how far I could get in this ladder of getting one degree after the other degree. And then, I liked it at university. I liked doing my bachelor's degree. And then it was clear that I continue with a master's degree. And that this is sort of a no-brainer if you are not really annoyed by being in university. And then afterwards, what do you do? And then I thought, it's nice at university. Why not do a PhD? Huh? It's nice. You will also get a job afterwards. And maybe even easier get a job afterwards, no matter where this might be. And then I did a PhD, and then I thought, maybe you can still continue to do a postdoc, because maybe you can become a professor. Huh? Let's just try it. If it doesn't work out, then I can anyways go back and get a job at one industry company, or like doing software, as Roland said, for example, in the worst case, sort of. Huh? And it was important for me to have like a fallback option, so that I have something else to do if this fails, and other careers might not have this. So other people in academia, they might only have the academic option then if they continue for so long. But for me, it was clear that I will just try it, and then if it doesn't work out, I get another job. But also from my like my peers and the people around me, they always said, okay, Julian, we see you as professor, you are so into this academia and you like this theoretical stuff and the scientific work, writing papers, applying for grants, going to conferences. We cannot really see you sitting in an office and having a boss that tells you which projects to finish for your customers. And and this is also how I see myself. Yeah. I don't know if it's the same for Roland or for others.
I think a big benefit of academia is the flow of time can be stopped, or it's different. We're different from in a company. And also maybe the social structure is different. I think there's less hierarchy, and I really enjoy going to conferences and speaking to my peers all over the world and just having fun, comparing notes. This is, I think this is quite rare, in at least this part of academia.
And did you always knew that you wanted to stay in academia, or have you had?
Yes. Oh yeah. I think it's really nice for mathematics at least.
Interesting to hear. You said something about the flow of time being different at university and at a company. What did you mean by that?
Well, I haven't worked at a company, so I shouldn't speak. But my impression is that there you have much more targets and deadlines, and here you can, there's teaching, which makes deadlines. And there are collaborators that want to talk to you, that makes for deadlines. But otherwise, you can just sit and think and talk to people for hours and hours. And I really enjoy doing that.
I see.
Yeah, which is also somehow necessary, right? The moment you are working on something that you don't yet know and you are working on discovering it, if you don't find some time to sit down and talk through your ideas and also explore what surrounds your idea to understand if you're going in the right direction or not, and to take a step back each time something is not working, without that time you wouldn't be able to get anything new, right? Mm. It's more like a walk in the dark where you're trying to figure out the path, and then it takes a lot of time to find where it is.
But there is a lot of time, so that's good.
And you don't have the pressure of needing to finish a product that some customer needs to pay your company money for, otherwise everybody around you will go bankrupt or so. So you have the time to go really in depth and then get to the bottom of where it happens and then push the frontiers of what is known a little bit further. And otherwise, if you just were to making a good product is also very difficult, but you don't need to make it optimal. You can make it good so that it can be sold, right? And then you can stop, because if you invest 2 more months, then another person can make it maybe better. So you rather finish it sooner than later. And in science, I think there's, as Roland said, this time to go deeper, dive deeper, and really find out why it is how it is.
I don't disagree that there is time, but I do see that there is, now I'm disrupting a bit the episode, but I do see that there is some pressure on producing a lot of good things in a short amount of time, both to show that you are good and to make if you wish, the system happy.
Publish or perish.
Publish or perish, for example, but also write grants and try to get funding and participate to national or international panels. It's a lot of extra activities in addition to the research that somehow are eating sometimes a big chunk in my experience of this time. So I'm curious to hear how much this is affecting you, or has affected you, or if it's never affected you, in fact.
Oh yeah, it can be very stressful indeed. But in some sense, it's like teaching. It's an extra job you also have to do, but it's not part of the academic procedure of thinking about your subject. It's more after the fact. Let's say maybe it can help to summarize what you have been thinking, but the thinking is still essential, and so I think it's important to challenge and cherish this and not let it be spoiled by all these other pressures. But you're absolutely right that there are some pressures, and you're asked to explain what you're thinking. And this is actually where outreach can help in training yourself to explain what you have been thinking. So outreach and grant writing, I think, is and should be related.
Yeah, it definitely does help you to structure your own thoughts, because you need to put the idea together. And you need to define what the goal is and what you want to do. Maybe it can be a completely different outcome, but at least you have a plan. And I also see this in the bigger context, like we are spending taxpayers' money, and we need to be responsible with that money. And so we have to compete with this, because not everything can be funded. So I need to tell people about my work, and I need to go also not just to my peers, but also talking math to strangers, right? So like to ordinary math people that have not such a big background in the science that I do every day, because these are the people that pay the taxes that I work with in that sense. And then I need to tell them why it's more important to research rockets landing on Mars than building a new swimming pool or so in their neighborhood. And I need to apply for money for that, because the swimming pool also has to apply for money. I think so it's fair. And I like the challenging, the competitive aspect of it also a little bit. So I like to apply for grants and see if it works or not. If you know that you get the money in the first place, it's not the challenge. Then it's not an accomplishment. And this is the same when publishing a paper or doing a research. If you know what will be the result, it's not that interesting, I think. It's interesting when you don't know before and then it works.
It sounds like sports.
Yeah, a little bit like sports. And you wouldn't like to watch a soccer game, even if it's your favorite team, if you know that your team wins anyways. That's boring, I think.
I don't know. Sometimes the journey towards something makes it. I mean, there are some plays that start by already the person dying, and then you already know how it ends, but you still want to know how it got so far. I mean, there are also other motivations, I'm saying, but it's definitely also a sporting aspect.
Do you guys think that this perspective is common among mathematicians more than other fields of science?
No.
Okay, yeah.
Maybe the pressure is higher in some subjects, like medicine or so, I think there, but also some more money maybe. But I really don't know, I haven't researched it. But it doesn't seem very uncommon. It's just that in mathematics, we're a science where they assume we need big machines, but we actually don't. So there's more money.
Yeah. That's a good point.
I think something interesting in mathematics is that it's one of those sciences where very often you can argue that there are applications to what you do, but the applications are not necessarily your aim or your interest even. Maybe the theory started there, or maybe the theory has connections with those applications, but in fact what is your main focus is developing the language, understanding where this language can bring, what is possible, what is not possible, and somehow developing the knowledge. And perhaps this knowledge will get back to the application, perhaps this knowledge will get back to some other application, but perhaps we will not know for quite some amount of years. And then there is always the question, why should we support this that is not giving us a product in the immediate time, or that is not leading directly to a product? And I think, of course, I'm biased, I'm a mathematician. I think it's a blind point of view, in the sense that there have been many instances in the past where not having an immediate application led to some important application decades later. Just think about all the number theory that led to cryptography. And cryptography is essential for everything we do nowadays. The relation with logic and computer science and computing, this is very strong. Modeling to create rockets, to create boats, to optimize engines. Many of these things didn't start with the application, yet many of this theory did start from discussing between physicists and mathematicians. At some point, there were just philosophers, right? Philosophers of science, but it was a discussion between people looking at the world and seeing how the world works, and people saying, okay, but if I take a step back from it, how can all the systems that behave like that in general work, and what can we infer from that? And is there anything that can work differently, and how? And then at some point it becomes completely disconnected from the world, but still there is that idea of the world getting behind, which I think is also something that came from your connection with knots, right? You can describe very abstract and interesting thing and classify structure and try to classify different type of knots, how many different knots there are and why and how they are related. And at the same time, it's something you can construct with your hand, and it's something that can have very practical applications.
True, yeah. But I think there's also, within mathematics, at least for me, there's also an internal motivation of cutting down all the nonsense that people create. Because I think as a mathematician, we are also kind of the gatekeepers for the theory, and making sure that the theory doesn't get diluted, but gets stronger by being more abstract. Because there's a danger if you make abstract things that they just become more and more abstract and nobody understands anything. And especially now when there's this drive to publish a lot of papers, there is an enormous outward force, so to say, in lots of theories being produced. But there should also be a counterforce that synthesizes theory and brings things together and makes them easy again, cuts down things that are actually not needed. Because abstraction is great, but not all abstraction is great. And sometimes it's even better to make it simple again.
That's a very interesting thought. That sometimes it's useful, the abstraction, it makes it stronger, but it's also useful to take a step back and simplify again. Do you also see it?
I think the quote is, I don't know who said it, as simple as possible, but not simpler, right? So you need to find out, okay, what's necessary to say, but don't let away too many things, but still be able to describe all the things that are necessary. And then for mathematicians, it's often going beyond that, like trying to describe more or thinking at a deeper level, which for some people might feel like, okay, why is this necessary? Why do you do this? But you don't know, maybe in the future this will be necessary, and then somebody comes along that needs a solution to a problem that has already been solved 100 years back, and they're happy that the people in the 19th century published on this thing. And then they find it, and then it helps them make a leap forward, which would have cost them 20 years to research or so at the time. So, yeah, and then in that sense, I agree to also what you said, Marcello, that, yeah, we don't know how far away we should be from this explicit application, and when this will ever be beneficial for what we do. But if you think about how, you said cryptography, like how the internet was made it into our everyday life, or like data compression, JPEG, and all these things, computers, then nobody in the beginning said, okay, the goal is to have computers for everybody and internet for everybody and cryptography. But yeah, it's a risk diversification, I would say. So you need to research certain things and then hope that in the end, maybe some of them will give a very good output for humanity. And that's risky. And that's why we need to apply for grants, because we need to convince people, politicians or other of our peers, that the work that we do has some implications eventually somewhere. Maybe it's in the long term.
Now, I don't want yet to move on discussing how you do outreach, but I want to head there slowly. Mm-hmm. And one of the things is that for many people, mathematics is this abstract art thing that possibly they have hated in school, or maybe they loved in school, but they decided that it wasn't for them. And sometimes, or at least some of the people I spoke with, they decided to not try mathematics, not because they didn't like it, but because they felt that it's too challenging, or you need to be a genius, or you need to already know and be good in maths at school to be able to do that. And so I'm curious about your track. I mean, both of you seem to have liked mathematics, computer science from a very young age. Did you have encounter some challenging, some roadblocks, or it was a very smooth path for you to say, I'm going there? Well, you at least, Julian, you moved from engineering to mathematics. And in fact, both of you, right? And Roland from computer science to mathematics.
I never got to computer science.
Okay, you stopped before.
But in school, I was a very poor student. I was not good at math. I liked what I thought was math, but the school math was not really agreeable. And I never really got it. I was not good at it. Programming, I liked in theory, but in practice, I also was very poor at it. In high school, I was not a very good student. And even first year mathematics, I had a hard time and had to redo all my courses. And only in second year, I caught on. But it was a painful process. And there was a big mismatch between what I thought was mathematics and what was taught as mathematics. And so I'm still trying to correct this now that I am a professor. I think we can do better.
What is it that made it click for you?
So I had my own motivations of what I thought was pretty and interesting, but this was this was only loosely related to what was taught in first year or in high school. Functions and calculus, all these tricks without any thought. And well, there's some fun to tricks, but then the tricks got harder and I didn't catch on, didn't know how to do an integral. I didn't feel very good. I was also busy doing other things, like 16-year-old are not usually only doing school things, right? So I was doing other things too. But yeah, I had a difficult time, but then I got up in undergrad and finally got what I wanted.
Was the same for you, Julian?
Yeah, I think what resonates with me is this feeling that it looks difficult while you learn it. And then 5 years later, retrospectively, you think like, okay, I do this easily. And it teaches you many things. First of all, it teaches you that you can learn and you get better at it. And the people that teach you this in your first year at university, they are not geniuses or gods. They're just a few years ahead of you. And it took me a while at university to realize that I always had a lot of respect for the teaching assistants, for the professors. I thought they know everything. They can solve every problem and they do it in a second. And if I ever sat down and it took me 5 hours to solve one of these integrals or so, and then the teaching assistants and the professors, they solved it in a completely different way, much faster. And then I felt, again, still very stupid. But then a few years later, I was doing the same tricks that they did. And that motivated me to have confidence in myself, in my own abilities, because you need to be a little bit crushed, I think, and then build up your confidence. And it's about perseverance, sticking to it, as Roland also said, like you need to go through it and then you improve. And I think the saying is, I think every reasonably advanced concept looks like magic if you don't know how to do it. So if you never solved any integral, then it looks like, okay, what do these symbols even mean to you? But I could say the same about a chemical formula or biological, like a cell or whatever, and because I'm not familiar with it. So it means if you sit down, and math is a lot about taking the time to think about it, to study the problems, then you develop the knowledge and the language also to describe problems, and then this helps you in the long term. And I think the main problem is that often people lose track on their way. Also, that happens a lot in school, that people miss a certain subject in geometry in 8th grade or whatever, and then they cannot catch up later because they have a gap. And then they give up on themselves, and then they said, I never was good at math. But they are maybe actually good, they just lacked a certain understanding of a certain subject.
Yeah, what helped me through all this was not so much the teachers, but reading some other books on math that I found in the library, like Martin Gardner, and people writing popular math books, like outreach books. Because to me, they were much closer to what I thought was interesting in math. And all these technical tricks, that's only if you already have a motivation for doing what you want to do. But if you're just trying to orient yourself, then these courses on how to do an integral are not especially helpful. Because why would you do that? Because there's so many things you could do. Why did you do this? But there were actually reasons why they did them. It's just that they didn't tell us.
Yeah, those are pretty nice and interesting thought. And I think this will lead straight to outreach, since exactly what you're saying, that your motivator was books by Gardner, which is one of the biggest probably examples of mathematical outreach if we think about the US, for example. Before then moving there, we have one question that we like to ask, since this is to show the human side of mathematics, and so the humans behind mathematics, the people behind mathematics, then I'm curious, what do you do outside mathematics? So last time I started with Julian and Roland. What do you do outside mathematics?
Well, I like to do music. I play the piano. I play the guitar poorly. I like to sing with my kids. So I have 2 kids, age 6 and 8, and we like to play around. And I also like to dance, like ballroom dancing, salsa dancing, this kind of thing. That's what I spent lots of my high school time instead of doing math. But I still like to go places. I always bring my shoes. And if I'm in Japan, I go down, see if I can go dancing. And it's always it's kind of like mathematics. It's a universal language. But unlike mathematics, it's very much in time. You have to do it in time. So the flow of time is definitely different. But this is something else I really like to do. I also like to draw and to try and sort of make art. But it's mostly nowadays with everything I do is sort of, all these hobbies are integrated with what I do with my kids, because I have to, I play with them, but I think this is a good way to spend time.
Yeah, definitely. Very musically hobbies also, except for the drawing, but yeah.
Sure, yeah. I think music is also very precise, but also very creative. So to me, it resonates well with mathematics.
I can imagine. Yeah. What about you, Julian?
Yeah. So I think I see myself also in a lot of things that Roland said, in the sense that mathematics is a lot about trying different things, and I also tried a lot of different hobbies. And I was dancing at one point and playing the piano at one point, and I had a race bike and was racing through the area. But I always found that you need something that is more convenient. And at the moment, I also always bring my shoes, but I go running. because running is wherever you go running, and also whatever weather it will be, you can go running, and so that's good. Every conference you can go running. Every country, when I go to Japan, I also bring my shoes and go running. And the nice thing that I like about it most is that when I run, and that's different for everybody, I cannot think about a lot. I can just run. And I cannot, if I have in my mind a problem about a proof or a concept or a theory or computation in math, I cannot do it while I run. I cannot think about it. And that's for me sort of releasing or letting the memory run empty and just recover sort of while you run. It's a mental, almost like a meditation exercise to run for me. And it can be fast or it can be intervals, but that's even better because then you can think even less. And then, as I said before, I like the challenge and the competition. So for me, it's always I need to sign up for competition. I run a half marathon here, and I have a target goal, and I want to make it. But then also you have your long runs in the weekend where you just relax, enjoy the landscape a little bit. And for me, it's important that I cannot think about my math from at work at that time. And in that sense, it's not really stressful to do this after a day of work, go to the running track. It might be raining, and then you go run your intervals. Also, the only important thing is then you need to stay healthy enough to go running. So I had some problems with my knee at some point. And then you notice that what you miss, and then you cannot not think in certain times. Then so the movement for me was always important, as a sort of counterpart balancing the job.
Yeah, some balance is definitely necessary.
Yeah.
I think for me, this is more like cooking. I also like to cook, and there you also absolutely have to pay attention. I think if I go run, I can still think math. But
maybe that's what I do wrong when I cook. I think too much. I think too little. Yeah.
There you have to pay attention to all the pots and the things and the process and so on.
I love cooking, but I find it so hard to multitask. Like if somebody speaks to me when I'm cooking, I just freak out because then I lose track of what I was doing and cannot figure out where I was. But I agree. In this, I'm more like Roland. I have to do so many things and keep track of them that then it allows me to space out, like when you run.
Mm-hmm. The hardest is if somebody wants to help cooking, then you really have to pay attention.
Yes.
Yeah, that's funny. I have the thing with running that if I run, I can't really think about stuff that goes too deeply. And just enjoying the scenery is then enough for the moment. Yeah.
Yeah.
It's funny that you have the same.
I guess it's about finding a balance for yourself. And when I started studying, then you get in a new environment, you have new hobbies, you have new people around you, a new social circle, and new tasks, new homeworks, everything. And then you need to find a new way to balance and juggle everything at the same time. And you get new hobbies. And for me, it was that then. And first I tried the cycling. But the cycling was not convenient because, when it's dark and rainy, it's not so nice, and you need special shoes for that, and you need your bike for that, and you don't bring your bike to Japan usually. So that's all different things. And then I decided running is just better for me, and that works. But for other people, it's maybe playing the piano. And I also was playing the piano, but then I think too much again. I was not playing the piano well enough so that I can just play and keep playing, but I was memorizing too much what to play, and then so it's always different.
Okay, now I think we've gotten to know you guys a little bit. So maybe we can head back or get along to the next part of the episode about talking math to strangers. You guys have both done different type of outreaches. How do you prepare when you're asked to speak at an event where there might be people that are not involved in your field of mathematics?
It depends on the event, I'd say.
Yeah, of course, yeah.
So what do you have in mind? I think the most important thing about a good outreach is to know your audience. So I guess you have to do some research on what your audience is going to be, what kind of experiences they had already. I think that's very important. And then maybe talk to some similar people about, they do a little pilot with someone, with your mom or whoever is similar to the audience that maybe with a student. I'm asked to speak at the Students Association, some symposium or something in Nijmegen. So I should do a tryout here with the first year students to see. But then if it's a primary school, you have to do a different kind of tryout, right?
Yeah, that's a good point, of course. kindergartners and first-year mathematicians require a different kind of presentation.
But I don't know about you, Julian, but I also enjoy just taking a risk, doing something strange, because you can. And because it's always an experiment anyway, so you might as well learn from it. Preparation is good, but over-preparation is also a problem. So getting some spontaneous thing is maybe just take some risk.
Yeah, so I did a lot of different events, and then after a while, I took a seminar on how to do outreach after several years, and then they told me how I should have actually done it. So you need to know what is your target audience, what is the goal that you want to communicate, and then you construct from that a few activities that are aligned with the target groups and the goals. It's similar when you do teaching or when you do research in a sense. But I always did it just like a hands-on approach. I was like, okay, what do I think I can do? And then I just did it. And then I learned it like this. I guess it's a little bit like cooking. You don't first take a cooking seminar and then make your first soup. I think you just say, okay, how do you do it? Okay, and then you put some things together. Maybe it's tasty, maybe not. You try it again, and then you gradually improve. So now I have a set of things, a set of activities and requisites that I bring. And I have some slides, posters, or questions that I can bring with me. And I have from this repertoire, I choose things. And then while you are speaking at the student conference or so, or while I'm at a science fair, then I talk about this or that, depending on who's in front of me. It can be that there's the school children. It can also be that they are the parents or that they are some students. So it might be very different. And then I need to adjust it to the target audience. So I guess with experience, you can have much more to choose from, and then you just do it. And as Roland said in the beginning, I made the mistake to always wanting to be perfectly prepared, to have like, okay, I have a perfect set of slides with timed transitions from one slide to the next, and then I say it, and then I make a break and show this thing, and then it's perfectly enough for this 20-minute slot or so. But then in the end, I found out it never works out as you plan it.
And you have all the proofs, right?
Yeah, and especially not with the children, because I had this one presentation for kids. It was in a sort of cinema setting, and I was at the front. And then from the second slide on, there was one kid that always asked questions on every slide. And I was like, yeah, I'm excited about your questions. But even after some time, all the other children said, hey, you always ask questions. We want to hear the rest. And then, of course, you run over time and then you can get frustrated. But it's nothing to get frustrated on if you get questions from the kids, because it's actually something good. Huh? So you want them to ask questions. So you need to plan, or you need to not plan for being on time too much, and then let it go, like float with the boat.
Yeah, create a nice atmosphere.
Yeah.
So my kids were there actually in this cinema setting at some point.
Yeah. Nice.
So I can say you created a really nice atmosphere.
Yes, good.
It was great
good to hear. But it's very different because we are always trained on being very scientifically precise, and we write papers that have to be completely bulletproof because we're building this foundation of math, right? And it has to be completely correct and everything. But then you need to let go of these things a little bit and then say, okay, I go out there and I see how it goes. And I try not to be intimidated by the fact that they are now like 50 rowdy kids or so. And you need to see how to get them to listen to you and all these things. But I guess what is best is if you just relax and then try to just take this as a nice moment to talk about your work and to involve the children or the audience.
Yeah, less is more, usually.
Yeah, definitely.
What was the first motivation that brought you to try and do outreach? Somehow we are in an environment that, at least in the past, had more of a focus in scientific outreach between scientists, between mathematicians, or teaching, so delivering knowledge to our students. And it wasn't that common to have people like Gardner, for example, that were instead focusing on the non-mathematicians or the aspiring mathematicians that were doing something else, so on all other people. What was your drive?
I would say there are two things. First thing is sometimes you have to do it. In a lot of grant applications, you have to do what they call dissemination, which means like you have to communicate the results of your research to your peer researchers. So that's if me talking about my scientific results to you. And then you have communication. That means talking about the implication of your work or the impact to people from other target groups. For example, industry or school children, parents, students, something like this. But for me, it was a little bit this feeling, okay, I would have liked as a kid to hear a talk about how these things work that I can understand. And I'm not talking about being like 20 years old as a student watching a YouTube video. It's more like as a kid, somebody coming there and saying like, okay, hey, I'm a mathematician. I have the feeling I never really saw a mathematician until I went to university.
Right.
And this is a problem, because how can I know that I want to become a mathematician if I've never seen one? I've always seen a soccer player or a firefighter, so that's why everybody wants to become that. Or maybe an astronaut. Everybody wants to become an astronaut, but there are only very, very few astronauts in the world. So it's a very small chance, and there are many more mathematicians. They work on similar interesting things maybe. So being a role model maybe for people, and then spreading this idea that this is a possible career, and to people that might not consider this career, maybe they live in more rural environments, or they are more away from universities. Their parents haven't studied, for example. They don't have these role models. And this excites me to bring this idea closer to especially children who then still have time to develop these ideas and study.
My first outreach activity was as a student assistant at the University of Amsterdam. I was asked by Jan van der Kraats, who is a famous outreach person in Holland, I'd say. But so he needed a student assistant to help with a master class for high school students, 5th classes, to explain something about number theory and the Riemann hypothesis. And so this was a 4-week event where we would meet online and do some activities and explore at this number theory at this level. And so we had a lot of fun doing that, and it worked really well and became a book later. I'm still doing things about that, but it's all started there when I was a master's student.
Oh, that's fantastic. So the book you have on the Riemann hypothesis actually started when you were doing your master.
Yeah. Just as a student assistant. So I had to write the text, and became a book. But the book was very much informed by all these interactions. So that we had this, it was called a web class, but it was really this online event where there would be one final meeting face-to-face at the end, but it was mostly online. And so the text was very important, and then the interactions online. And so we ran this for 4 years or so, and then it grew out of that.
Wow.
It's a good experience. But also my bachelor thesis, I think, led into this. I wrote a bachelor thesis on a topic together with the same professor, Jan van der Kraats. And the topic was also very visual. This book called Indra's Pearls, with lots of beautiful pictures. I can highly recommend, even if you're not a mathematician. It has lots of cool pictures, and also computer code, how to draw them. That was also kind of an outreach effort by the people writing that book, but it's also a very serious math book. So I think this book is also for me a very clear example of how to do such things. You involve some computer code, some pretty pictures, some heavy mathematics that nobody has seen ever, and some jokes.
Nice. If you send me the reference of your book and this other book, we can add it to the episode listing.
Yeah.
And from what you said here, that for you, Julian, your favorite audience is kids. Somehow it relates very closely to your aims, right?
Yeah, I think it's interesting to talk about the research with everybody, I think. Usually when you're in any social situation, and then, okay, what are you doing? And then you say, I do math, then people are less interested than before you say that. But if you then can present your story and you can say what you do and they're actually interested, it's cool to do that, because also it shifts people's perceptions of what mathematicians do and who mathematicians are. As I said, it's not just about the content, it's also about yourself being a role model for mathematicians, because maybe people might not know that many mathematicians. And then it's about different target groups. But I find it very interesting talking to kids, because you really see the fascination and this genuine curiosity in their eyes when you talk, because they have really never seen like a mathematician talking about rockets before. So my typical setup is I go somewhere where I present my work as like the mission to Mars, the race to Mars. Okay, so we want to go to other planets, and okay, we need a rocket. So what does the rocket need to have? How we need to design the rocket, and where do we need to land on Mars? And then, okay, we need to go through the atmosphere, we need to land, and then how do we do that? Do we design the best spaceship that can go to Mars? And then I have this Lego rocket, which is a 1 meter Lego rocket, and I think Marcello has the same, so he knows it quite well. And then I bring this, and then we can look at it, we can take it apart, and the students can say, okay, where are the astronauts sitting in the rocket? They can touch it, they can open it, and it excites them. It gives them an idea. Okay, I want to learn about this more. And then we get to the point, okay, but how do we do this? How can we know beforehand how we can land on this planet? And then, we need to somehow compute this beforehand. And so we need mathematics. Okay, good. So maybe it's a good idea to think about how we can learn these mathematical things. That's the sort of idea, the root that I want to plant in the children, in the sense, the message that I want to bring across, because most people don't think about math as the first thing when they think about rockets. They want to become an astronaut, right? And I want to tell them, no, there's not that many astronauts. It's very unlikely. It's like becoming a soccer player like Cristiano Ronaldo. So it's not very likely, or a rock star. Maybe you want to have also an interesting job, but that is maybe more likely, and you still do the interesting things that you want to do.
And Roland, what is your favorite audience?
I don't know. I like to mix it up. But I do like to challenge myself and the audience by picking something that's slightly inappropriate in the sense of being too difficult. So I like to pick something that's difficult and then try to cheat, make it seem easier, and then hopefully people will take a step to approach. So, but that goes for all audiences, I think. Yeah, I don't know. Children are fun, but it's also fun to try to challenge grown-ups to behave like children. But children are definitely the role model for what your audience should be like. I find that playing games also helps, and maybe grown-ups can be children again if they are allowed to gamble or play games, because then at least some of us still have practiced that way. If you ask them to engage in a scientific conversation, then it's a loss. But if you ask them to play a game, then maybe they still want to win, or at least enjoy. So I think this is another good entry point. And so here I must quote The Winning Ways for Your Mathematical Plays. It's another great book where mathematicians have tried to describe lots of mathematical games, or try to say mathematical things about ordinary games. There's a lot of fun to be had there.
Oh, very interesting. Actually, I would like to pick up on your cheating part. First of all, I kind of like the idea that you say that keeping it fun, making it playful is a good way to keep the audience, right? Not making it too serious so you can just play with it. But then you mentioned at some point you like to cheat and make it seem simpler, or try to get the idea. And this is my biggest fear with when approaching outreach. I don't have that much experience, but very often when people ask me about what I do, the way I explain it with some example of application of what I do, and try to use them to explain that there is a whole language to describe these things, and then this allow in one shot to describe all of them and discover what is possible or not. And this is the part that I like. But
motion of the planets or so.
Never, for example, the motion of the planets, for example, satellites, for example, the falling cat. So you can find also the fun examples. But then my fear is that very often it's so necessary to oversimplify what you're doing. And then I feel I am somehow being dishonest with my audience.
Like a
I
magician.
understand that it's necessary, but on the other hand, I don't know, I still feel bad. I'm so used to speak to mathematicians where you can simply say, even if you hide some details, you have to just say things as they are in their abstraction and in their context, that when I have to explain them in a way that I start to remove the assumption or hide them or remove what I'm really doing and cheat my way in it by using an example or something that relates to it, that somehow, I don't know, it's my problem. I have this issue, and I like to understand your approach with it, because it seems that you can use it in a very efficient and effective way to then bring across your ideas.
Yeah, I guess it's a difficult balance to strike, being close enough to your research and not lying about what you do, and still being interesting enough or very close to an application or a problem that people can relate to. But I think they can always, or they should always be able to relate to the bigger picture, I think. So if I say, okay, we want to have multiplanetary humankind, or we want to have rockets that land on other planets or so, this is something that people think, okay, yeah, that sounds interesting. At first, yeah, okay, let's talk about this more. And of course, I'm not myself designing a rocket in my backyard, but at least I'm contributing a small part somewhere in this whole machinery of this whole thing to it. And I'm also then telling the story that, okay, it's of course not just me doing this on my own, but there's probably a million of people doing all sorts of different things. And this is also a message in itself, that people need to learn this. They are not solving the whole problem themselves. So if you give the example of like the movement of planets, then you are not doing this alone and solving all the problems. Yeah, it's also clear. And I think, I don't know what the expectations exactly are of people when they listen to presentations like this, but they should not expect that with our maybe sometimes decades of experience in this job, we are working on something that we can explain to them in one sentence. It should not be the case, because we're working only on this for years and years and years. So how can we then specifically say what we really do every day in this one paper that we are writing at the moment? This is difficult, but we can tell them how this fits into the big picture. Because we should, or we will probably have some strategy or grand plan, or like where do we want to be in the future in 10 years with our work, if it all works out. And I think that's good enough, and it gives people hope and it gives people vision. And if these people grow up, then maybe in 10 or 15 years, they will enter our fields maybe, and then we will maybe be there also. And then they can help us continue that.
I think you make a really good point that something that you've studied for years, you cannot really present in, let's say, half an hour to the same details as you study it.
Yeah, at least you need to make some way of abstracting this, or finding, let's say, conveying the key results or the main message or something like this. But of course, not everything should be interesting for everybody. But that's the same also when you go to a conference and speak to experts in your field. You cannot convey everything already. So how can you possibly do that to high school students?
Do you sometimes get questions that surprise you, like from children, that you're like, oh, this is something that I've not thought about it?
Always. When I ask the children, how would you make this rocket slow down so that it doesn't crash when it comes back? They say, yeah, why don't we use a parachute? And I say, yeah, that's actually a very good question. Why don't you use a parachute? And then I tell them, yeah, we are a little bit too fast for the parachute, for example. Then they say, why don't we just pull the brake, for example? And then I say, yeah, we don't have a brake. And then they say, why don't we accelerate in the opposite direction? We have a rocket in the front and then push us back, sort of. And then, yeah, you need to think about it. You need to find the good reason first. And then say, okay, then we need more fuel to carry the rocket. It's too heavy. And then it takes you further and further. But so kids are usually very creative with these things. They ask things that a normal scientist wouldn't even dare to ask, probably because they think it might be stupid. This is always very interesting. And I want to encourage children asking more things. And I mean, our work is also about this curiosity, inquiring why it could be the case. Not just making it work, but why does it work? It's not the engineering approach. It's not continuous improvement that is good enough so that it works. It's more like, what is the optimal shape and why? Or the optimal solution maybe. Is there even an optimal solution maybe? The engineer doesn't care if there is an optimal solution maybe. They would just want something as good as necessary. And this is also a message you can convey to children. And yeah, it's important to ask questions.
This reminds me a lot of something that my PhD supervisor used to tell. One of my supervisors, Andreas Nauf, was doing these lectures for kids where he was presenting mathematics. It could be algebra, it could be analysis. It was simple ideas of mathematics presented to kids. Mm-hmm. And each time he would come out saying that he had such creative questions and answers to things, many of which he would have not thought it by himself. And it was super fun and somehow invigorating, energizing to have these meetings with the kids because of all this energy that they brought up in the lectures, something that we don't see in our lectures usually.
Yeah. And also it tells you if you understand the topic well enough, because if a kid can ask a question and I need to think, okay, I'm quite sure it's wrong, or we cannot do that, but why? Why can't we do that? Why is it wrong? It seems so intuitive for me that this is wrong, but actually what is the actual reason to it? And then I can fake a reason and tell the kid, oh no, that doesn't work because, and then I give a fake reason. But then I sometimes go home and think what was actually the reason for that? Or is that even true what I said? I need to study this deeper. And then, you go into the nitty-gritty details of this. But this is how research works. You provoke questions, and then you find out better ways to communicate this or to improve your research.
But coming back to the cheating, I think outreach still, if it's live, it's still a performance. So it shouldn't be confused with a lecture. It's a performance. So in a performance, you're allowed to cheat, because what is decisive is the impression that you give. Not if you get people to think, then that's more important than getting all the details right. So I think there are several kinds of outreach. There's the live performance, and then there's writing a book. And even in a book, it's kind of, if it's a popular book, it's kind of a performance in the sense that you want to give people an exciting read, and not necessarily an education per se. So I think what I also enjoy about teaching, but also outreach, is this performance of almost like if you're playing a piece of music. So I like to play music, and it's exciting to play for a bunch of people. It's also exciting to say something about your research. But then, just like if you play a tune, you should keep the beat, right? You should be in tune. So I think music is a good thing to keep in mind. If or telling a joke, there's a rhythm to a joke. There's a rhythm to music, and there's also a rhythm to any other performance. You have to gauge your audience and see. And even if it doesn't make any sense what you're saying, if you get the rhythm right, they will go with it. And then we're also mathematicians, but that's somehow not so important at that time. But of course, what's great about mathematics is that there are so many hidden treasures that nobody has dared to really explain, because maybe they don't understand themselves, or they have given up on ever explaining this because you need a PhD to say that. But often you don't need a PhD to say that. If you don't need to do all the details, but just give a glimpse, you can definitely give a glimpse of some really advanced topics. And if you can't, then maybe you should do some more research. So for me, it's definitely also a drive to do some more research to really understand and get some glimpse that I can then explain. Maybe not all the things in between, but this glimpse should be something that could be explained or at least performed. So that's what I mean by cheating.
Thanks. I mean, both your answer actually make me feel already much more comfortable with this idea. I have another curiosity. So I know that, Julian, you have the big rockets and you have lots of Legos and now also puzzle with the rocket. Each time I enter in your office, Roland, you also have an office that is full of ropes and polygons and pieces that stack in many different ways, story polygons and tessellations and whatnot. So both of you have lots of gimmicks, if we want to use more practical terms. Are those also used, well, in one case I know that they are used for outreach, but Roland, also for you, is this something that you use for outreach, or be it with students or with other people outside mathematics?
I'm always looking for new gimmicks. I'm really happy with this one gimmick that I thought was even better than bringing a gimmick, is to have people use their body, because your audience, whatever the audience is, usually has a body. And so mathematics in 3 dimensions is difficult, but people are very used to surviving in 3 dimensions, but never think about hitting a target or eating a bite out of your sandwich. We never think about that as a mathematical act, but it's actually very, very, very difficult to do. All these things are very difficult to do if you start thinking about them. It's like landing a rocket on Mars, just eating a bite out of your sandwich. You have to aim well, you have to open your mouth, you have to time, you have to gauge. And so making people aware of their own body in a mathematical sense is, I think, a fun gimmick in itself, which is somehow a little bit more direct in a sense than bringing stuff. But of course, I do like to bring stuff. But this is, I think, something that we haven't explored so much. And of course, I like dancing, so it's, for me, it's maybe slightly more natural. But your body can do lots of strange things, and if you think about those motions mathematically, well, that is, I think, a very interesting meeting ground for strangers and mathematics to talk maths.
Yeah, I guess it comes down to somehow visualizing what you're talking about, because a lot of people, like you perceive a lot visually, and you want to maybe touch something, or you want to be moving yourself, as Roland said. And it's often about having a model of the reality or the concept that you want to present, whether that be a knot or, in my sense, it's a rocket. And I cannot bring the rocket full size, so I need to have a scaled down version of that. And then it's still about, okay, people know that rockets are probably large, but then you still have to convey the idea of how large is that actually. Yeah? And then when you say, okay, it's 110 meters, people say like, okay, yeah, what does that number mean? And then I say it's as large as the church tower, or the bell tower of the church or so. And then they know, oh, okay, I know how tall this tower is. If I stand on the market square in Groningen, then I know the Martini Tower. And if I'm in front of that, then I know how large the tower is. And then the astronaut is as small as me, because I'm human size. So yeah, then you have a perception of what's going on. And I like to bring this model. And the fact that it's Lego is because Lego produces these things. And so I got it. And probably a large portion of people have fascination for Lego since they grew up. So I would like to buy a lot more things. And I know we share this, Marcello. So you have many more objects of this. You can make many more episodes about that. But I was fascinated always by this idea of Lego being, you can construct something. You can also construct something new. And it's just your own fantasy that makes things come to life, sort of. And the interesting thing then is it addresses not only kids, it also addresses the parents, because the parents know Lego from before. And every generation has played with Lego, I think. So you can address a lot of people. And for me, it's incredible to construct one piece of, like a rocket or a spaceship, out of 2,000 different Lego pieces. As a kid, that would have been my biggest dream, to do something like that. And now I can do it, combine it with work and with outreach, and that's great for me. Yeah, so I would like to do this more and more, and it's perfect. And then you can use it as a model to outline your research maybe. And yeah, of course, then I say, okay, this is the big rocket, but I'm not working on the whole rocket. I'm only working on a small thing. And I like this. And I'm constantly hunting more things. And recently I got this, this is 3D puzzle type of rocket, which is similar idea. And ideally, it's something that the people can interact with. And I don't just want to bring a movie, because then people just watch it and that's it. But it's also the mixture of different media, different things. Maybe you can have a set of questions or a questionnaire, and maybe something people can touch or play with, like play a game. And then depending on the event, the audience, you can mix it up.
I was wondering, you guys talk a lot about projects that you're doing currently. Is there any project that you're working on or have somewhere in your head that you would like to implement later on?
So I'm going to give a lecture for math camp. So that's vierkant voor de wiskunde. It's, I think, students 8 to 12 or so. And so I'm going to challenge myself to, I have a lot of time still, but I'm going to teach them what I used to teach the third-year students. So that's a risky thing to do, but I think it's possible. So that, my plan is to teach them about space, and in mathematics this is called algebraic topology. But they will have no idea what I would say there. But I think I found a way to get all the algebra and all the topology out of the way, and then it's just space. And so I think we're going to have a lot of fun there, and this might even be a book project that I've started. So trying to really go down to the basics of, suppose you want to build up space out of nothing. And now it sounds like fundamental science, but it's something that maybe also touches a general audience, I hope at least. So what can you do? This is a little bit like graphs and networks. Well, everything is a network, some people say. But space is not really a network, because you have something spatial. So it's not just lines and points, people knowing each other. There's kind of networks or computers connecting to each other. But it's something more than just points and lines. It's triangles as well. So at the beginning of the episode, I said something about millions of triangles. But I think we can, just by using language, everyday language, we can speak about how triangles relate and how triangles fit together. And so this way you can really dream up lots of strange places and spaces and try to walk around in them. And I think this is a really interesting exercise to see how far we could get with just playing with triangles.
Sounds ambitious, but also very nice. What about you, Julian?
Yeah, so for me, I have a repertoire of things that I do with my rocket, and people are usually very excited about Mars and rocket science and so on. But now I worked on this wave propagation, so water waves, tsunamis, and coastal protection and things like this, and doing mathematical modeling and simulations for that. And it's in the same line with avalanches and erosion, things like this. And I want to include this more in my outreach activities. And unfortunately, there's not a good Lego model of like an ocean or something like this. But I'm thinking in this direction, like how to tell people, okay, well, how do waves and water move, and how can we model something? Can we predict how tall the wave will be without actually involving maybe water, or maybe I do involve the water, and then that's not clear because I don't know. And the rocket, the thing is already, how do I transport it? And then make it as simple as possible, but not simpler. That's the idea. And then going more into another direction, basically building up the repertoire. And then the plan would be the long term, that I involve also more and more my PhD students in these activities, so that I'm not there alone, but I have maybe different projects. So I have like, okay, let's look at here. There's a rocket science example. There's like a coastal protection, whatever thing. And then it's the same. We need fluid dynamics, we need math, we need to compute this somehow. And we have different examples of that.
Since we mentioned Japan and since you mentioned wave, I think Lego has a Hokusai wave model as a painting. It's still a start. So if you want to keep the Lego thing.
At least, we can maybe, we as customers of Lego, as frequent customers, we can maybe make a request that we can have something like this. Yeah.
Just lots of blocks in a big box.
Yeah.
Lego avalanche.
But so let's steer the discussion a bit into how your employer, our employers, and our community look at this outreach. I mean, you have done a lot and you have many ideas for the futures. And so I'm curious about what's your experience with the recognition and the rewards toward public engagement and outreach.
Yeah, so from the discussion here, you could probably tell that Roland and I really enjoy doing these things. For us, this does not feel like work, but of course it is work. And we do this in our work time, but we also have other things to do in our work time. And most often the work time is not enough. So we do this over time, basically. And it's not really recognized much in the sense that we would get any benefits from doing more like this from our employer. There's no financial incentive for us. There's no incentive for promotion really that this would be good, or there's not really a lot of support for this. I would say it's mostly relies on the fact that we are willing and able to sacrifice our time for doing that in most of the cases. And I think there needs to be a shift in perception, and there needs to be more recognition, more value attached to these types of activities. And I said it already, sometimes grant proposals, they require that you do this. But then I think the employers only want published papers, acquired funding, and maybe students that graduate or so. And it is important for us to really tell our university how much this influences the people. I mean, we are educating the next generation, like mathematicians. We are educating students. But where do these students come from? Yeah, they are going to school. So we need to tell them maybe you want to study math in the future. So we need to think long term. And that's why we need more recognition for these outreach projects.
Yeah, I fully agree. I'd say that I don't really get more incentives to do more outreach or to write another book or so. No, it's in some sense actively discouraged. You could say that there is some benefit in making teaching more fun, but it's mostly free time. We spend some of our free time doing this. It should be different.
Do you think this is changing? I mean, if I look at least here in the context of the Netherlands, there is this movement, rewards and recognition, that would aim at changing the way our work is evaluated, to have a full-rounded evaluation that includes all our talents and all the things we do as part of the job, which includes more teaching, collaborations, and in this sense also impact in the form also of public engagement and so on. And this has directly or indirectly at least led to at least more focus or more investment in support like Science Links or Scholarian Academy for our university, which might not be perfect, but at least they are growing. They are trying to figure out how they could help us. Do you think things are changing, or do you think we are still pretty far away from seeing proper recognition of outreach?
I think it is starting to change, but it sometimes has also a little bit the touch of sort of like greenwashing, okay? Like we have it in our policy that we encourage scientific communication and we like it, and the university puts it on their LinkedIn webpage and they put it on their website as news. But then is it really recognized? Or do I really get this as a bonus point when I have my interview for promotion? Or is it really that they say, oh no, you don't have enough publications or so? I mean, I don't want to say that we shouldn't publish anymore, but I think if we invest time in something that is useful for the university, they should clearly, and they are using that to make their own sort of news coverage, then it should be valued more. So we should be careful to push this forward and to continue this, because it goes in the right direction, I would say. Yeah.
But we're not there yet.
Yeah, exactly.
I mean, I can't disagree with you. I mean, even looking at what it took to start the podcast, and Marit is doing it basically of her own free will. Here we are.
It's the same.
And it's basically the same. I try to acquire funding to support her here for the work we are doing, but what we could get is the support of the faculty and of FSC Radio, that I want to thank publicly here for the equipment to record the podcast. At least we have professional equipment and we have a decent sounding audio, but that's about it. Everything else is coming from our own time and evening.
This basically happens in our free time. Yeah. At the moment. Why? Okay, we are at work, but when we go back to the office, there will be emails waiting for us and students, and so this is a good point.
And good outreach requires serious thought. It's not that's something to emphasize. It's not you can just show up and say some things. No, you have to seriously think about what you're going to do. So not less than giving a presentation on a conference or even writing a research paper. It still requires serious thought, just in a different way.
I had no clue that representation and outreach was looked at this way by the university, because I'm not involved in that in any way. It's kind of sad because, as you say, like every outreach also benefits the university and mathematics as a whole. So yeah, I definitely agree with the incentive to change that view.
Of course, the university would say we value that, we have it in the policy and so on, and that's true, and things are changing. But I think we also need to see how much money goes into this. What are the funding budgets for that? When Marcello says about funding for a podcast, we are not talking about tens or hundreds of thousands of euros, which are completely normal for even the smallest research project. We are talking about hundreds of euros maybe. So it's a very small amount. And no, there's not even money for that. So it's a different scale, and it still generates a lot of impact. But the problem with this impact is it's difficult to quantify. It's difficult to say what is the output of this podcast that we're having here, or of Ona giving a presentation somewhere to high school students, because you don't get citations for it, or you don't get research funding or so. So in that sense, having a counter for the listeners of this podcast or so, where you can say, okay, how many people does this podcast reach, already is something like, okay, maybe more people will listen to this podcast than that people read my paper. Okay, so and then then it's useful to some community at least.
Well, thank you very much. I want to take the opportunity to thank you both for coming here, and Marit for helping me to prepare the episode, figure out what we want to do, and arranging everything. And we wanted to close with one last question to you both, which is, so if you think about some mathematician, think of our student or our PhD students or some postdocs, some other professors at our university or other university that want to start doing public engagement. And what would be your suggestion on where to start, and what are the do's and don'ts that you would give them? Roland?
I think it's important to connect to things you like to do, to make it personal. And so that depends on what this person is. But it's important to, just like in this podcast, we try to show that we're actually people, not just mathematicians. I think that helps to bridge the gap if you speak to a non-mathematical audience to show some of your humanity and whatever that is. So when I did my PhD, I didn't want to speak mathematics to my audience because of a family and friends. So instead I did a little dance to show my knots, and it's still on YouTube if you want to see. But I think this was a very successful thing in that I didn't have to speak to them, but I could still speak to them in a way that was really personal to me and sort of relatable. And so everybody is different, so everybody has their own things they like to do. And I think it's important to connect what you're trying to get across, to connect it to yourself and what other things you like to do, because that helps.
Thank you very much. Julian?
Yeah, I think the most important part about starting with is to just do it. And it doesn't have to be perfect. You don't need to have a perfect script of what you want to do and everything well prepared. You just start with something small, pick a subject that you like, an object that you like, bring it, talk to people about it. And it's not about creating the perfect image and you will think, oh, this thing didn't work, that thing worked, and then you can iterate from it. But I see a lot of people hesitating to do it because they say, okay, but what example should I pick? Or what should I start with? But then it's about, okay, if you never start, then you will say the same thing in 5 years still. So you start small and then you have more ideas and you think about it and you can improve. So just do it.
That's good advice, I think. Then with that, we will end this episode. I would like to thank you both for your time. Even now, I know that you do this voluntarily, sort of. And thank you to the listeners. I hope you enjoyed this episode, and we hope you will also tune in next time.
If you like this episode, please consider sharing it with your friends and on your social media accounts.